Hello, my name is Marion Sudvarg. I'm a postdoc at Washington University in St. Louis, and today I'll be presenting a paper written with Gill and Sanjoy Baruah titled Improved Implicit Deadline Elastic Scheduling. In the modern world, real-time systems increasingly execute in dynamic environments. An example of this is in the quickly developing domain of self-driving cars, where perception pipelines must process data from multiple sensors, such as the pictured LiDAR stream, in a timely fashion. The computational workloads and latency requirements depend on external factors. A crowded city street, for example, presents a more challenging environment than a highway in the countryside. This means that real-time systems must adapt to maintain temporal guarantees even on overloaded computational platforms. And so elastic scheduling, which was originally proposed by Buttazzo and others at RTSS 1998, has emerged as a framework to enable task adaptation to guarantee schedulability in the face of overload. Elastic scheduling allows tasks to reduce or compress their utilizations. Under this framework, each task, tau sub I, is characterized by some parameters including u sub I max, which represents its maximum desired utilization. This is the utilization of the task when it executes normally in an uncompressed state given sufficient computational resources. U sub I min represents a constraint on the task's minimum utilization. This is the utilization necessary to guarantee that the task maintains safe execution or produces correct results. Finally, E sub I is called the task's elasticity, representing its relative adaptability. Often more important tasks are considered less elastic. Now, if the system is overloaded, the idea of elastic scheduling is to decrease each task's utilization from its maximum proportionally to its elasticity until the system becomes schedulable. However, task utilizations are constrained to remain above their minimums. So now let's discuss how this utilization compression may be realized. This can be done in two ways. The first is to extend task periods, and this has been shown in the context of control systems by Buttazzo and others in their 2007 paper. Also, in our recent paper at RTAS 2024, we demonstrated that this is viable in the context of atmospheric aerosol monitoring and simultaneous localization and mapping, also known as SLAM applications. Task utilizations can also be decreased by reducing their workloads, for example, by reducing the amount of input data to process or by early termination of an iterative refinement algorithm. And we've demonstrated this technique in the context of real-time gamma ray burst localization in a 2023 RTCSA paper. And there's also a piece of the aerosol monitoring application that can have its task workloads reduced by changing the number of masks applied to an image processing task. And we will show this in an upcoming RTSS paper. Next, we need to consider when utilization might need to be compressed. First, of course, is during offline schedulability analysis. If the task system cannot be scheduled on the target platform, then utilizations can be decreased before the system is deployed. However, there are several scenarios where compression needs to happen online. For example, like we discussed with self-driving cars, the external environment can cause changes in task workloads. Furthermore, available computational resources may change online, or new tasks might be admitted to the running system, or in a mixed criticality system, task utilizations might be compressed to avoid job dropping when a critical task overruns, and we discuss this in an upcoming RTNS paper. The point that I would like to highlight in all of this is that because utilization compression may have to happen to enable online task adaptation, the algorithms that assign the new task utilizations under the elastic scheduling model must be provably efficient during online adaptation. And so our goal in this work is to present new, more efficient algorithms for elastic scheduling of implicit deadline tasks. These include linear time, online adaptation for schedulability analysis that checks total utilization against a bound, which we apply to uniprocessor scheduling, multiprocessor fluid scheduling, and partitioned EDF. We also demonstrate a binary search technique for more complex analysis, which includes heuristic partitioned EDF. And finally, we present a quadratic time algorithm for elastic scheduling under global EDF. Let's begin with uniprocessor scheduling, for which Liu and Leyland demonstrated schedulable utilization bounds for earliest deadline first and rate monotonic priority assignments. In the original elastic scheduling algorithm presented by Buttazzo and others in 1998, recall that the idea is to reduce task utilizations proportionally to their elasticities until the system becomes schedulable. Now, the sum of task utilizations minus the desired utilization bound is the total amount of compression that needs to be applied. Then, since each task's share of compression is proportional to its elasticity, we can compute the utilization assignment for each task to make the system schedulable. But keep in mind that tasks also have minimum utilization constraints. In Buttazzo's original algorithm, if compression would bring a task's utilization below its minimum, it has to get set back to the minimum, and the remaining tasks have to be compressed even more. Now, because compression requires assigning a utilization to each task, but this loop might have to rerun as every task's utilization is brought below its minimum, the total time ends up being quadratic in the number of tasks. So the question we wanted to ask in this paper was, is there a faster way to do this? The key observation we make here is that there is an amount of compression needed to bring each task to its minimum utilization. So if we sort tasks by this value, we know the order in which they will reach their minimum utilization constraints. And so in this paper, we demonstrate an algorithm that allows compression in a single traversal of the sorted list. And moreover, the sort only has to be done one time. After that, admission control or other online adaptation, which is what we want to be efficient, can happen in linear time. So to analyze the time to admit a new task to the system, we implemented this algorithm to run on a single core of a Raspberry Pi 3B+. We first implemented Buttazzo's original algorithm, measuring the median time to admit new tasks on a system already running between 4 to 49 tasks. And we did this over 10,000 different randomly generated synthetic task sets, and we plotted the medians here. So then when we do the same measurement, but this time using our new proposed algorithm with a linked list for the sorted task list, you can already see a significant improvement in execution time. Now if we move to using a binary tree for the sorted task list, well, now it runs even faster, since the binary tree enables logarithmic time insertion rather than linear time insertion of the admitted task. Finally, we implemented the sorted list of tasks as an array, which runs the fastest, because even though it requires linear time insertion, there's no pointer following. And so the result is you can see that our algorithm runs much faster than Buttazzo's original algorithm as the number of tasks grows. And our algorithm remains much faster when comparing worst case times. So next, we applied the same approach to fluid scheduling. Fluid scheduling is a convenient abstraction for multi-core scheduling with a utilization bound equal to the number of processors. Every task is assigned a fraction of a processor corresponding to its utilization at each instant in time, so tasks make proportional progress at each time instant. A set of tasks are thus fluid schedulable on M processor cores as long as the total utilization does not exceed m and individual task utilizations do not exceed 1. Since we're only considering implicit deadline sequential tasks in this paper, the second condition is automatically met, and our problem is still just one of compressing to a utilization bound. To evaluate whether the results shown for uniprocessor scheduling still hold for fluid scheduling, we measured the execution time of our algorithm as a function of the total minimum and maximum utilizations and the difference between the two of our randomly generated task sets. We observed no execution time dependence on these parameters, leading us to conclude that the results should extend to fluid scheduling and our new algorithm will remain efficient. Next, we considered partitioned EDF. Fluid scheduling is easy to analyze, but impractical to implement in a real system. In contrast, partitioned EDF is straightforward to implement, but it requires a partition of tasks onto M cores where total utilization on each core does not exceed 1. And this is algorithmically equivalent to bin packing, which is NP-complete in the strong sense. So now the question is, how do we think about elastic scheduling in the context of NP-hard schedulability analysis? Well, let's revisit the original model of elastic scheduling. Recall again, task utilizations are decreased proportionally to their elasticities until the system becomes schedulable. Well, what this implies is that we can represent the amount of compression by a term which we call lambda, where each utilization is then compressed by an amount equal to lambda times its elasticity while constrained to its minimum. Now the goal is to find the smallest value of lambda where there is a schedulable partition for the resulting utilizations. In the original algorithm for elastic partitioned EDF scheduling, presented by James Orr and Sanjoy Baruah at RTNS 2019, the idea is to perform a linear search over values of lambda with some tunable precision epsilon in the range from 0, representing no compression, to a value of lambda that takes all of the tasks to their minimum utilizations. Then, for each value of lambda, utilizations are updated, and then pseudo-polynomial bin packing heuristics are used to find a schedulable partition. Lambda is then increased by epsilon until a schedulable configuration is found. We propose two alternatives to this approach. First, we observe that we can binary search over the range of possible values of lambda, enabling logarithmic time rather than linear time search for the smallest value. We tested several configurations of randomly generated synthetic task sets with 9,000 task sets for each configuration. More details can be found in the paper about what parameters are used for each configuration, but the idea is that each one represents different numbers of tasks, different numbers of cores, different maximum utilizations, and different total task utilizations. And as you can see, our binary search enables almost 2 orders of magnitude speedup compared to the original linear search. Next, we consider using a utilization bound for partitioned EDF. In a 2013 paper, Sanjoy Baruah showed that the first fit and best fit decreasing bin packing heuristics guarantee a utilization bound on M processors of m+1/2. Now, although this bound is pessimistic, in other words, oftentimes the heuristics achieve a better utilization bound, this allows us to use our quasi-linear compression algorithm. So we compared the binary search algorithm to this utilization bound algorithm, and we can see that the binary search is more optimistic. In other words, it enables more task systems to be compressed to a schedulable configuration. However, the utilization bound provides significant speedups, running up to 25 times faster than the binary search, which itself was up to almost 100 times faster than the original linear search. So the utilization-bound approach is beneficial in cases where a very fast decision needs to occur. So for example, in a mixed criticality system, this utilization-bound based approach enables fast adaptation in the case of overruns. And the added pessimism is no worse than the alternative of job dropping of low criticality tasks anyway. Okay, so finally, in this work, we considered elastic global EDF scheduling. Under global EDF, only the active jobs with the earliest absolute deadlines are picked for execution. Global EDF is then schedulable on M-cores so long as the total utilization does not exceed this bound. Now notice that the utilization bound in global EDF includes a term that subtracts the maximum among the task utilizations. So let's call this maximum U sub j. Okay, so if we rearrange this equation, we can use the insight that we can replace the task tau sub j that corresponds to this utilization U sub j with another task that scales the utilizations and elasticity of the original task by a factor of m, the number of cores. And if we do this, then in our new transformed task system, we end up with a schedulability condition that looks like this. And as a matter of fact, this gives us a compression problem with a utilization bound. Now, the challenge here, the problem, is that we don't know which task will have the maximum utilization after compression. So our solution is to just run the algorithm, trying all of the tasks. And whichever selection of task for tau sub j gives us the smallest compression, while still keeping tau sub j as the maximum utilization after compression, is the result that we keep. And so now, since the initial sort needs to be done only once, we have a linear time compression for each selection of tau sub j, which ends up giving us a quadratic time algorithm. Okay, so in conclusion, elastic scheduling adapts task utilizations in the face of overload. Online adaptation, however, must be fast. So in this paper, we've presented fast elastic scheduling algorithms for implicit deadline tasks, including a quasi-linear time algorithm for uniprocessor scheduling that enables linear time online compression, including for admission control of new tasks. We've extended that algorithm to fluid scheduling. We've proposed two approaches for partitioned EDF, one which is a binary search approach, and one which is a utilization bound approach, which is much faster while having somewhat less ability to schedule task sets. And finally, we proposed a quadratic time algorithm for global EDF. And as future work, we'd like to think about whether we can extend these techniques to other scheduling algorithms. For example, the hyperbolic bound for rate monotonic scheduling provides a more optimistic schedulability bound than Liu and Leyland's original utilization bound. We'd also like to think about extending to multi-core partitioned rate monotonic scheduling or multi-core global rate monotonic scheduling. Finally, we'd like to think about extending these techniques to the priority-driven algorithm PRID, sometimes called global EDF-K, which is an alternative to global EDF that provides somewhat better schedulability. So thank you very much, and I hope this talk made you want to read our paper. I also hope you won't hesitate to contact me if you have any questions at all. And thanks again, and I will leave this slide up for just a few more seconds so that you can write down my email address or access my website via this QR code. Thanks again.